Hello there. Hey, we're working on another section of 8.3. This 8.3 volume section just goes on and on. Today you're learning a new method that you did not learn in AB. It's called the shell method. And the shell method is rather clever and useful when you're working around a vertical axis of rotation because it allows us to continue to work in terms of x, which is nice because then we are not solving equations for x. So I've got a little video that helps introduce the idea of why shells. Why would a shell method be handy? And I want you to see the visualization behind it. So let's watch this quick YouTube. We're just going to try and get the first 2 minutes of it, and then away we go with doing a couple problems. So got it keyed up here. Okay, so we're going to jump in and we're going to work with this cylinder idea and how that is kind of transferred into what we call shells. So let's start with this first problem on your notes. It says find the volume of the region bounded by the following functions rotated about the y-axis. So I think first thing we're going to have to do is get down the x squared minus 4, and this one's going to be minus 4. So obviously we get negative 4, 0, and then if I put in 1, I would get out negative 3. If I put in 2, I'd get out 0. And if I put in 3, I get out 9 minus 4, so 3, 5. This gives us a parabola. I'll do my best. Getting a little wavy there. Right, there's our parabola. And then we've got the x-axis. The x-axis and x equals 2 and x equals 3. Oh, the surface of the laptop is so slippery that it makes tracing on it somewhat difficult because it just wants to slide around. All right, we'll get that locked in. Here's that parabola. So really the region that we are spinning is going to be this region right here. I'm going to erase the x equals 2. It locks it in there, but that's fine. We don't really need it. Now, what this is going to do is we are going to rotate about the y-axis. So our axis of rotation, maybe you want to note that this is our axis of rotation, the y-axis. So we're rotating about that. And if you can imagine, we'd have this light blue region here spinning around the y-axis. And let's see if we can drop in what would be a representative shell. So I'm going to make my representative slice right here, kind of that rectangle that we were talking about that's going to rotate about. It's got to come over to this point, doesn't it? And so I'm going to even draw that vertical. Well, that was very, very crappy there. Let's try it again. Draw in that left side. 3 units high is what I had before, so I'm going to try and keep my same 3 units high. And now I'm going to make it look like a cylinder. And then this, of course, would come down. And there it is. Now, this does have a little bit of thickness, so I'm going to try and sketch in this thickness of my cylinder. It's got that little bit of edge to it, doesn't it? So that would be how thick it is. And if I did this over and over, following the height as it changes, I could fit all these in there and it would create that that volume piece that we're looking for. So what I need then is when I unroll this shell, I get a rectangle that's just got just a little bit of thickness to it. But the thickness of this is dx, isn't it? It's got a dx thickness to it. And it has a height, and that height is determined by my function. And so it is following the x squared minus 4 all the way down to the x-axis. So minus 0, I could do top minus bottom, which I guess I could throw it in there. There's the top minus the bottom, but it's still just going to be x squared minus 4. And then what is the length of this? The length is that circumference that was outlining our shell as it rotated about the axis of rotation. And we know the formula for circumference. Circumference is 2 pi r. Now I just need to, I'm going to draw in my r. Right there is my r, which is a distance of x. So in this case, my circumference is at 2 pi x. Okay? And that really is all I need to do in order to get the thickness and the volume of the shell. So here you see the formula, 2 pi r. So that creates the length of a rectangle. The height is captured by the f of x function. So this is going to most often probably be 2 pi x, and then the height will be our f of x function, and then multiplied again by the thickness dx. And that's really a quick version of shells. So I'm going to put my 2 pi out front, and 2 pi in the integral will be in terms of x's. So I need to go from, I need to know this spot here, which, oh, it crossed at 2, didn't it? And then we finished at 3. And we have 2 pi r, 2 pi x. And then the height is f of x. So I have x squared minus 4 dx. Yeah, that's all it looks like. We could, of course, integrate this one by hand. Let's get it started. We'd have an x cubed minus a 4x times the thickness dx. Integration, so 2 pi out front. 1/4 x to the fourth minus 2x squared. Yeah, that would generate 4x, wouldn't it? And we want to integrate from 2 to 3. Oh, what the heck, let's just keep going. This is so much fun. So I'm going to have 1/4, 3 to the fourth, 3 to the fourth, 81, minus 3 squared is 9. 9 times 2 is 18. Take away, now let's go down to the bottom, put 2 in, 2 to the fourth. 2 to the fourth is 16. 16 divided by 4 is 4. Minus 2 goes in, 2 squared is 4. 4 times 2 is 8. And that is where I came up with, I had 2 pi times 81 fourths minus 18, a minus 4 plus 4. So it looks like minus 14 on that. And this will come out to be 25 halves pi. Okay? So that is shell method. Just imagine all of these shells taken in here as, I should have made it go further out, but just kind of a nesting of shells to create the volume. The backside one, find the volume of the revolution of the region bounded by the curves, x squared plus 2, got that showing. X plus 4, got a linear function cutting through our parabola. So I get this green region because the y-axis is also acting as a bounds. I've shown you one representative cylinder sitting in here, our shell, and we draw the picture with a cross-section perpendicular to the x-axis. The radius of the cylinder is going to be x once again. And so it'll be some horizontal distance measured by x, and the height is going to be our functions. I was going to put f minus g, but they weren't really labeled that. I'm going to say top minus bottom instead. So let's talk about top minus bottom so that we can capture the length or the height of our shell. So I'm going to go blue function linear, which is going to be x plus 4, take away the parabola, which is x squared plus 2. You know that top minus bottom will always get you a vertical length, won't it? So that's super handy. And now, if we think about our representative rectangle, unfolding that cylinder, this length here would be 2 pi x, and the height is x plus 4, take away x squared plus 2. This would be our height. This would be our length. And then we go and multiply it by the thickness, which is in this case going to be a dx thickness. That drives us into our volume formula of 2 pi x times the height, x plus 4 minus x squared plus 2. We should be able to simplify that. Notice there's no big R squared or anything like that going on, as in disk and washer. We just get 2 pi r times the height. And we could probably work this through. Well, let's simplify it a little bit. Why not? I'd have x plus 4 minus an x squared. So I'd have a minus x squared, a plus x, a minus 2 plus 4, so plus 2 dx. Then I'd send that x through, giving us negative x cubed plus x squared plus 2x dx. Integration by hand, always good to practice. So I'd have negative 1/4 x to the fourth plus 1/3 x to the third plus an x squared. I almost wrote plus c. I forgot to do my bounds. Oh, goodness. Well, we got to get those bounds on there. And our bounds, we want to roll from 0. I got to go figure this out. So we started at 0, right? Then we'd have really skinny cylinder in the inside of this, and then it's going to get gradually larger and larger following our function coming up there. They intersect. Where do these two things intersect? Well, let's calculate it out. X squared plus 2 equals x plus 4. I can take everything to one side. X squared minus x minus 2. That would be an x minus 2 and an x plus 1. So they intersect at x equals 2 and an x equals negative 1. It's the x equals 2 that I'm interested in. So now I'm going to integrate from 0 to 2. Let's add those on our integration. And then bounds 0 to 2. And we can plug those in. Trust me on this one, you get 16 pi over 3. All right, there's the shell. You can see shell is really not too difficult and lovely to do when you're spinning around a vertical axis of rotation. I thought that was kind of a cute t-shirt. Homework. Are these, I think there's 3 problems. 1, 4, and number 13. Now 13 is going to be a little tricky because you're rotating about x. So now everything has to be in terms of y. So this one you will have to convert. In your r is this now. That is talking about a y height. So r equals y in this case. All right? And then you'll just have to go right minus left. So this linear function, solve it for x, and then go 2 minus that, and that should help you get that problem correct. Because I made a note to myself, a lot of people mess that problem up. All right, have a good day. If I can get it to shut off.